Hello, analysis students. So, I owe you a little bit of information about subsequences. In particular, I want to tell you about the subsequential limit of a sequence. So let's start with this. Last time, in some sense, we proved the Bolzano-Weierstrass theorem. What is the Bolzano-Weierstrass theorem? The Bolzano-Weierstrass theorem says that if some sequence x sub n is a bounded sequence, then x sub n has a convergent subsequence. Well, what does a convergent subsequence mean? A convergent subsequence means something of the form x sub n sub k, where n sub k itself is a strictly increasing sequence of natural numbers. And let's just remind ourselves a definition. Given a sequence x sub n, a number x is called a subsequential limit of xn if there exists, I can write out the words. Oh, come on. There exists a subsequence. Let's even give it a name. X sub n sub k, which converges to x. So what I want to start studying, what the lim sup and lim info are all about, is they're about the study of the set of all subsequential limits. And it's not necessarily standard notation all over the place to use blackboard bold L to denote the set of all subsequential limits, and so I'll always redeclare it when I need it. But I'll try to resolve the variable name blackboard bold L for the set of all subsequential limits. And let's start by, if I want to talk about the supremum and infimum of a thing, I need that thing to be bounded and non-empty. Those are the types of things that have sups and infs. So, let's prove that. Let xn be a bounded sequence, let blackboard bold L be the set of all subsequential limits, then I claim that blackboard bold L is non-empty and bounded. Well, let's prove that. Let's let xn be a bounded sequence. Let's let L be the set of all subsequential limits of xn. I want to prove that L is non-empty. How do you show a set is non-empty? You need to exhibit an element of that set, or otherwise deduce that an element has to exist. This will feel somewhere in the middle. I will definitely produce an element of L. Well, this will also be super straightforward. The sequence xn is bounded by assumption. Well, what do I know about bounded sequences? They have convergent subsequences. By the Bolzano-Weierstrass theorem, I conclude xn has a convergent subsequence. But what do I know about convergent subsequences? They have limits. Since this is a convergent subsequence, I will let L be the limit of that convergent subsequence. Oh wait, I've just explicitly constructed a subsequence, namely this subsequence, x sub n sub k, to give it a name, which converges to x. That's exactly the definition of what it means to be a subsequential limit. So x is a subsequential limit. L is the set of all subsequential limits of x sub n, so x is in L. Since L has at least one element, L is non-empty. L might have only one element. That would be just fine. Okay, I need to prove that L is bounded. We'll call by assumption that x sub n is bounded. So I can declare U to be an upper bound, L to be a lower bound. And it seems awful convincing that if U is an upper bound, then xn certainly can't have any subsequences which converge to a thing that's greater than U. U, I claim, is an upper bound for L, and little l, this assumed lower bound, is a lower bound for L. Well, let's try to do it. So if you want to show that two things are bounds, what do you need to do? You need to show, so maybe I'll shift over here, change colors. What is it that I want to show? I want to show that for all x in the set of all subsequential limits, L is less than or equal to x is less than or equal to U. If I want to show something is true about every element of a set, I will start by considering any element of the set. So let's do that. Let's consider any element of the set X, and I need to show that this is true. Well, let's try to unpackage definitions. By the definition of the set L, X is a subsequential limit of xn. Right, because L is the set of all subsequential limits. By the definition of a subsequential limit, that means there is a subsequence I could even give it a name, x sub n sub k, it doesn't matter what you call it, which converges to x. So I think I'm going to put just a little bit more elaboration into this step. So by assumption, U and L are upper bounds for the sequence xn. So let's just say what that means. So for all n in n, L is less than or equal to x sub n is less than or equal to U. This sequence n sub k is a sequence of natural numbers. So that means that for all k in n, n sub k is in n. And you'll have to forgive my penmanship. I am extremely non-used to using surfaces. For all k in n, n sub k is in n. So n sub k is in n, so this implication holds. That conclusion holds. So L is less than or equal to x sub n sub k is less than or equal to U. Oh wait, so that means for every term in the sequence, I have an inequality. I have a limit law says that I can take limits of inequalities. The limit of a loose inequality is a loose inequality. The limit of a strict inequality is still a loose inequality. By limit laws, I then see that L is less than or equal to the limit of x sub n sub k. Maybe I'll even specify this is the limit as k goes to infinity. Sometimes it's nice to specify that. Is less than or equal to U. But that limit is by assumption x. X sub n sub k converges to x. As x is the limit of x sub n sub k, I conclude that L is less than or equal to x is less than or equal to U. So notice, what did we do? We considered any x sorry, you can't see what I point at unless I do so explicitly. I considered any x in the set of subsequential limits. I did some work. I eventually concluded that L is less than or equal to x is less than or equal to u. So that means this is a proof that for every x in L, L is less than or equal to x is less than or equal to u. That's exactly the definition of what it means for u to be an upper bound for the set of subsequential limits and L to be a lower bound. Thus, the set is non-empty, because we checked that already, and it's bounded. So it's non-empty and bounded. That completes the proof. But what's the point? Why do I care? Well, since L is non-empty, and bounded, the fact that the real numbers are complete gives me as a consequence the fact that, sorry, I'm a little bit lost just where to go next. Here, the next page. Well, no, I don't have explicit space there. Okay. Since L is non-empty and bounded, the completeness of the real number allows me to conclude that L has a supremum and an infimum. Now I'm ready to actually define what the namesake of this particular bit of the notes is. Let Xn be a bounded sequence, L be the set of all subsequential limits of L. Aha, so I know that that set is non-empty and bounded. The limit superior of the sequence Xn, which I will denote with the notation lim sup, lim for limit, sup for superior, or in the textbook's notation, they'll use the word limit, but they'll draw a line on top of it, is the supremum of L. So the limit superior is the supremum of the set of all subsequential limits of Xn. Conversely, the limit inferior, or lim inf, or lim with a line underneath it, is the infimum of that same set. Well, let's see, if you happen to like the notation lub for least upper bound, use that. If you like the notation gulb for greatest lower bound, use that. Both are fine. There's an extra credit post for the same day as this packet is supposed to go up, which explains another way of understanding lim sup and lim inf. So our mark, this lim sup of Xn is not the same as the supremum of the set of everything that looks like Xn. And this is something that seems, I think, well, that in order to see that a claim like this is false, you just need a counterexample. In fact, most sequences will be counterexamples, whatever most means. But let's just take this sequence, for example, xn equal to 1 over n. We've computed the limit of this sequence. Maybe computed isn't the right word. We've proven that that sequence converges to 0. So, if a sequence converges to 0, then any subsequence must converge to 0. So any element of the set of all subsequential limits is a limit of a convergent subsequence. We've just seen every subsequence converges to 0. So every subsequence converges to only 0. So the set of subsequential limits is the set containing only 0. Finally, the supremum of the set of everything that looks like Xn is the supremum of the set of things that look like 1, 1/2, 1/3, 1/4, 1/5. That supremum is 1. Right? 0 isn't even an upper bound on this set. Well, I guess I'm missing one thing here. So lim sup of Xn is the supremum of the set containing only 0, which is 0. So, something to notice first, which will be pretty light. Lim_sup and lim_inf can completely determine if a sequence converges. So here's the claim. Let xn be a bounded sequence, then lim_sup is equal to lim_inf is equal to L, if and only if xn itself converges to L. So there are two things here. If you can somehow compute lim_sup, and you can compute lim_inf, and they turn out to be the same, then you know the limit of the sequence. So in some sense, that maybe feels a little bit like a squeeze theorem kind of argument. It can be interpreted that way. And the other conclusion is that if xn converges to L, then you know what the lim_sup and lim_inf are automatically. So let us prove. So first, I guess the forward definition. Suppose the lim_sup is equal to lim_inf is equal to L. I need to show that xn itself converges to L. Well, let's do it. So let's suppose that xn is a bounded sequence and lim_sup is equal to lim_inf is equal to L. Let's suppose, for the sake of contradiction, that the sequence, x sub n, does not converge to L. Well, let's see what we've actually assumed. So I'm going to do as I do sometimes in class. I'll go into the space that is the margin, and I'll figure out what that even means. Come on. Alright, well, this will do. So I want to see what that means. So not x sub n converges to capital L. And this is going to be informal. This is, if you like, just notes to the side. So what does that mean? That means not, and then I'm going to put the definition of xn converges to L. It is not the case that for all epsilon greater than 0, there exists a big N, such that for all little n bigger than big N, absolute value of x sub n minus L is less than epsilon. And, well, now I know how to negate this using the standard logical calculus. It is not the case that for every epsilon bigger than 0, some stuff happens. So there must exist an epsilon for which that stuff doesn't happen. And what is that stuff? That stuff is there exists an n such that some stuff happens. So that means I need to I'm going to assume that there does not exist an n such that some stuff happens. So that means that for all n, that stuff does not happen. And what is that stuff? Well, the stuff is that for all little n bigger than big N, and so it is not the case that for every little n bigger than big N, this inequality happens. So what does that mean? That means there must exist a little n bigger than big N so that this does not happen. So there's what I've assumed when I assume that x sub n does not converge to L. Let's write that down. X sub n does not converge to L. By negating the definition of the limit, I see that this means that there exists an epsilon bigger than 0. That epsilon could be 5, that could be a fifth, such that no matter what choice of big N I make, there exists a choice of little n bigger than big N, so that absolute value of x sub n minus L is bigger or equal to epsilon. So here's something that I see. So I'm going to use the set capital X to refer to a particular subset of natural numbers. The reason for this choice of variable name is lacking. I will define the set big X to be the set of all n in N such that the absolute value of x sub n minus L is greater than or equal to epsilon, I will study that set. That's looking really bad. There. I will show that this is an unbounded subset of n. And the reason is basically just the line right above. So I've declared that choice of epsilon, these two epsilons are the same. Well, let's suppose that is too big. Suppose some number big N is an upper bound. And I'm going to get so immediate a contradiction that this is really even more of a direct proof. Suppose big N is an upper bound. Let's see, by this line, so what am I going to do? I will label this line with a little star. By star, there exists a little n bigger than big N with absolute value of x sub n minus L bigger or equal to epsilon. But then check it out, because x sub n minus L is bigger than or equal to epsilon, n satisfies the condition that defines the set. This number n satisfies that condition in gold. But because it satisfies that condition in gold, I conclude that n is in the set X. Oh wait, but this little n is bigger than big N. As little n is bigger than big N is not an upper bound for the set X. And what was the whole point of showing that this set is not bounded above? I can start listing elements in increasing order. So I can pick an element of the set, the smallest element, n1, then there's a second element, n2, there's a third element, n3. Since this set is not bounded above, I can keep going on forever. So I can list the terms of x1 at a time as n1, n2, n3, and I can put them in increasing order because this is a subset of natural numbers. Oh wait, but that gives me a strictly increasing sequence, doesn't it? Well, there's x sub n sub k is then a subsequence of x sub n, and what do I know? I know that for every k in n, x sub n sub k, not x sub n sub k, n sub k is in the set X, because n sub k is by definition the kth element of the set X. And what does that mean? That means that n sub k satisfies the defining condition of the set X. It satisfies this condition. So what does that mean? That means that absolute value of x sub n sub k minus L is bigger than or equal to epsilon. Okay, so I do promise that I'm getting close to having the result. It may not seem like it, but I am very close. So n is bounded, so the subsequence x sub n sub k is bounded. A subsequence of a bounded sequence is itself still bounded. So I can apply the Bolzano-Weierstrass theorem to the sequence x sub n sub k to find a subsequence of that subsequence. So there's a subsequence x sub n sub k sub j. So now j is the independent variable, k depends on j, n depends on k, which in turn depends on j. Such that x sub n sub k sub j converges. Let's let x be the limit, and just for specificity, of x sub n sub k sub j. Well, let's see what I have. For every choice of j, n sub k sub j is in x, because n sub k is in x for every choice of k. What does that mean? That means that the absolute value of x sub n sub k sub j minus L is bigger than or equal to epsilon. Oh, but now I can use limit laws. The limit of an absolute value is the absolute value of the limits. The limit of a difference is the difference between the limits. So by passing to the limit, I conclude that the absolute value of x minus L is bigger than or equal to epsilon. In particular, x is not equal to L, because this epsilon is bigger than 0. So the absolute value of x minus L is bigger than 0. That means x is not equal to L. So by the trichotomy law, there are two cases. Either x is bigger than L, or x is less than L. Oops. All right, cool. I'll get a contradiction in either case, but maybe I'll explain the contradiction first. So because L is supposed to be the limit superior, L should be an upper bound on the set of all subsequential limits. But x is a subsequential limit. So x being bigger than L means that L is not actually the limit superior, is not the supreme of the set of subsequential limits. It's not even an upper bound. So that's where we will go. All right, there, those cases were labeled. So since x sub n sub k is a subsequence of x sub n, that number x is a subsequential limit of, x sub n sub k sub j is a subsequence of x sub n. X is itself a subsequential limit of x sub n, so x is in the set of subsequential limits, blackboard bold L. But L is the, let's see, limit superior of xn. So that means that, in particular, it is an upper bound on the set of subsequential limits. But wait, I claim this is a contradiction. Why is this a contradiction? Well, x is greater than L. And in order to be very confident, I'm going to flip is the wrong word. I'm going to go back to the previous page and make sure that case A is the case that I mean. In case A, x is bigger than L. Yeah. And let's just check that that is actually a contradiction. L is the limit superior, so it's an upper bound for the set blackboard bold L. But x is a thing in the set blackboard bold L, which has x bigger than L. Yeah. So L is not actually an upper bound. In case B, x sub n sub k sub j is a subsequence of xn, and x is a subsequential limit of xn. So that means x itself is in L. Presumably now I want to use the opposite. L is the limit inferior of xn. So it is the infimum of the set of all subsequential limits. It is a lower bound for L. This is itself a contradiction, as x in case B is strictly less than L, so L is not a lower bound. Nice. Okay, cool. So now let's do the obvious one. And this proof will be super easy. Let's assume that xn converges to L, and show that the lim sup is equal to the lim inf is equal to L. Alright, so that's the supremum and the infimum of the set of subsequential limits. So that means I better study the set of all subsequential limits. Assume that xn converges to L. Let L be the set of all subsequential limits of xn. I want to show, well, how am I going to proceed? I'm going to completely classify what the set of subsequential limits is. Maybe it's pretty believable that it's probably exactly just the limit of the sequence xn. It's just L. So I'm going to take anything in the set of subsequential limits. I'm going to prove that it's actually equal to L. So, well, let's do it. Since x is in L, x is itself a subsequential limit, so there exists some subsequence x sub n sub k, such that x sub n sub k converges to x. Wait. So x sub n sub k converges to x. On the other hand, x sub n sub k is a subsequence of x sub n, and I know that x sub n converges to L. Theorem 2.6.2 is the theorem from the previous packet, which says that if a sequence converges, then all of the subsequences converge to that same number, the limit of the sequence. So that means that x sub n sub k converges to L. We've proven that if a sequence converges to two different numbers, then those two different numbers are the same number, so that x is equal to L. Since x represented an arbitrary element of blackboard bold L, that means that the set blackboard bold L is a subset of the set containing only L. So let's just check that we actually did that. I started by considering any x in blackboard bold L. Check. I did some stuff, not very much. I concluded that x is equal to L, so it's in the set containing only L. So yeah, that's a proof of that set containment. So now let's go the other way. L is the only element of this set, so if I can show that L is in the set blackboard bold L, then I'll be done. Well, that's really easy. L is the limit of x sub n, so x sub n is a subsequence of itself, so L is a subsequential limit. So that means L is in blackboard bold L, and I get the other containment. Alright, so now let's compute the lim sup and lim inf that I claimed I would. So that means that the lim sup of xn, that's by definition the supremum of the set blackboard bold L. So if you like, I'm here. The supremum of the set blackboard bold L, well, I know what the set blackboard bold L is. It is the set containing only L. The supremum of a set containing only one element is itself that element. Similarly, lim inf of xn is the infimum of the set blackboard bold L. Sorry, my actual hand-drawn blackboard bold L's are not very good. Is equal to the infimum of the set containing only L, and again, that is equal to L, exactly as I needed to show. Great. So let's keep on going. So the next result says that the lim sup and lim inf are actually subsequential limits. So this is going to be repeated, some of these ideas, when we eventually introduce a new idea called the closure of a set. So let's do it. As is my wont when I have a claim about suprema and infima, the two proofs will be the exact same. So I'll just prove it for the one. So I'm only going to prove that the limit superior is itself a subsequential limit. And let's remember this was 2 lectures ago. Lemma 2.6.7. Maybe I can go down here. Lemma 2.6.7 read it yourself, but informally, what does it say? It says x sub n is a subsequential limit. Nope, xn is a sequence. A sequence cannot be a subsequential limit. X is a subsequential limit of xn if and only if for every epsilon bigger than 0. So no matter how close you want x sub n to be to x, for every big N, no matter how big you want the subscript to be, there exists an n bigger than big N. So there exists some choice of subscript bigger than this choice big N, so that absolute value x sub n minus x is less than epsilon. So what does this say? This says that a number is a subsequential limit if and only if, no matter how close you want the sequence to get to that number, it does get that close to that number, and it gets close to that number over and over again. No matter how big you set that big N, there's a term after that big N so that x sub n is that close to this number x. All right, so according to lemma 2.6.7, if I want to show that S, the lim sup of xn, is a subsequential limit of xn, then what do I need to show? I need to show that for every epsilon bigger than 0, and for every choice of big N, there exists a choice of little n bigger than big N, such that the absolute value of x sub n minus x is less than epsilon. And I'm going to prove this by contradiction. So there's the thing that I want to prove. The thing that I just wrote in black is the thing that I want to show. If I'm going to use a proof by contradiction to prove that, well, I know what I need to do. I need to show, well, and I'm going to assume that there exists some epsilon. All right, when you negate a universal, you get an existential. And there exists a choice of big N. Oh. It doesn't matter what you call your variables, but it does when you have like pre-written notes. So there exists some epsilon bigger than 0, and there exists some big M, so that for every choice of little n bigger than big M, not this holds. And so what's the negation of that? Well, it's absolute value of x sub n minus x greater or equal to epsilon. Nope. So this is why it's so very important for me to give these with an audience. X itself isn't actually a variable, like it's not a declared variable. It was a dummy variable down here, but that's not part of the actual proof. That's not even something you would include. S is the thing I'm trying to show as a subsequential limit. So there's what I have. That is what I know right now. There exists a choice of epsilon and a choice of big M. Notice those don't depend on anything. Those are just some constants. So that whenever I take little n to be bigger than big M, I get that inequality. Well, now let's just push through. So let's consider any subsequential limit, x in the set Blackboard bold L. Then there is a subsequence x sub n sub k of x sub n such that x sub n sub k converges to x. Okay, so that's fine. I'm going to try to take advantage of this statement. No, not that statement. This statement. So if I can get n sub k to be bigger than big M, then I'll be done. Then I'll be able to make a conclusion about x sub n minus s. Well, that's easy to arrange. I know that n sub k is a strictly increasing sequence, so as soon as k is bigger than big M, n sub k will be bigger than big M. So by 2.4, which is this, I get to conclude that absolute value of x sub n sub k minus s is bigger or equal to epsilon. I don't know how big epsilon is, but it's some positive fixed constant right now. Passing to the limit, because x sub n sub k converges by assumption, absolute value of x minus s is bigger than or equal to epsilon. So it must be either that x is bigger than or equal to s plus epsilon, or less than or equal to s minus epsilon. And all right, you can draw a picture. Well, yeah, sure. Draw a picture of a number line to convince yourself of this. So what does this mean? I know that absolute value of x minus s is bigger than or equal to epsilon. So if there's s, and there's a length epsilon, there's that same length epsilon, x has to be somewhere over here. So that would give me case 1. Or x has to be somewhere over here. That would give me case 2. If you wanted to prove that rigorously, it would also be straightforward. It would just be the standard manipulation of absolute values and inequalities that we do a lot. All right, so let's get a contradiction in each of these cases. So either x is bigger than or equal to s plus epsilon, or x is less than or equal to s minus epsilon. And the first one is obviously problematic. In the first case, x is bigger than or equal to s plus epsilon is bigger than big S, and recall that is the lim sup of xn. Oh, but that means this is the supremum of blackboard bold L. So that means x is itself a subsequential limit of xn, so it should be in blackboard bold L. But it exceeds the supremum, it exceeds something that's a known upper bound. So that's a contradiction. So case 1 can never happen. So it must be that case 2 is the only thing that happens. So it must be that for every x in blackboard bold L, x is less than or equal to s minus epsilon, and notice that is strictly less than s. Wait. That means that s minus epsilon is an upper bound on the set blackboard bold L. So I found an upper bound on the set, specifically s minus epsilon, which is strictly less than s, which is, by the definition of the supremum, the least upper bound on L. This is a contradiction. So it must be that the thing that we assumed for the sake of contradiction is false. So let's go way back. What did we negate for the sake of contradiction? We negated this thing that we wanted to show. So it must be that that thing that we assumed was false is in fact true. So it must be that for every epsilon bigger than 0, and for every choice of big M, there exists a little n bigger than big M, such that absolute value of x sub n minus s is less than epsilon. By lemma 2.6.7, which apparently was even called the reformulation of the notion of a subsequential limit, I get to conclude that s is a subsequential limit of xn. Cool. All right, so there's one last thing that I think is worth talking about. And, well, I guess I don't have to look too closely at the time. The next theorem gives me a reformulation of the limit superior and of the limit inferior. So here's the reformulation of lim sup. The reformulation of lim sup is that for every choice of epsilon and every m in n, there exists some little n bigger than big N such that absolute value of a sub n, which is the name of the sequence right now, minus L is less than epsilon. So notice, that's exactly what it means to be a subsequential limit. And for every epsilon bigger than 0, there exists some big N in N, so that as soon as little n is bigger than big N, a sub n is less than L plus epsilon. And then something super similar happens with limit inferior, except that there's a typo. And that's not what I wanted to emphasize, though. This inequality changes. There's the only actual difference between those two claims, those two statements. Again, I'll only prove the claim for lim sup. The proof is identical with some inequalities flipped. Not all of them, just some of them. For lim inf. And it's not all of them because, right, you can see that it can't be all of them. Those two stayed the same. Okay, proof of forward direction. Let a sub n be a bounded sequence. Let L be the limit superior of a sub n. By the thing we just proved, L is a subsequential limit of a sub n, because the limit superior is a subsequential limit. So by this reformulation of subsequential limits, it must be that for every epsilon bigger than 0, there exists a big M, such that for every little n bigger than big M, absolute value of a sub n minus L is less than epsilon. That's exactly the false condition of the theorem. So the false condition of the theorem follows. Next, I need to show that for every epsilon bigger than 0, so what remains to show? It remains to show that for every epsilon bigger than 0, there exists some choice of big N, so that for all little n bigger than big N, a sub n minus a sub n is less than L plus epsilon. I apologize for all those typos. So let's suppose, for the sake of contradiction, that that were not the case. And I'm going to build a set capturing all of the indices where this inequality fails. So I will let X be the set of all n in the natural number such that a sub n is greater than or equal to L plus epsilon. I claim that this set is not bounded above, and let's even try to explain why. In fact, I think I want to change this a little bit more. I don't want to put that for all epsilon. I think I would rather, right here, say, consider any epsilon bigger than 0. So now epsilon is a fixed number, but it could be any fixed number. So let's suppose, for the sake of contradiction, that it were not the case that there exists some big N such that for all little n bigger than big N, a sub n is less than L plus epsilon. I'm going to show that this set is not bounded above. Well, let's see if big N were such an upper bound, then what would I conclude? I would conclude that for all little n bigger than big N, well, that little n would be bigger than an upper bound on the set. So for all little n bigger than big N is not an element of X. But this X is built explicitly in set builder notation. So to not be an X means that that inequality must be false. So by the definition of X, I would conclude that A sub n is less than L plus epsilon. Oh wait, but let's just repackage that. So what does this mean? Thus, if X were bounded above, then there exists some choice of big N, namely an upper bound, such that for all little n bigger than big N, absolute value of A sub n, nope, there's no absolute value. A sub n is less than L plus epsilon. Oh, but that's exactly what I assumed was not the case. Contradicting assumption. X is not bounded above. And here's why I care about the set X not being bounded above. It's the same reason as I cared about sets not being bounded above in the past. If a set is not bounded above a set of natural numbers, then I can list the elements one at a time. X is equal to n1, n2, n3. So nk is equal to the kth element of X. Aha, that means A sub n sub k is a subsequence of A sub n, which satisfies that for every k in n sub k is in X, and so, well, look at the definition of X, set builder notation, A sub that n is bigger than or equal to L plus epsilon. So now I can play this standard game. A sub n is a bounded sequence. A sub n sub k is a subsequence, and so it itself is a bounded sequence. So A sub n sub k has a convergent subsequence, A sub n sub k sub j. That thing converges to some number. I'll give it a name. I'll say that the limit is j goes to infinity of A sub n sub k sub j is equal to A. Well, for every j, n sub k sub j is in X, so I have the inequality A sub n sub k sub j bigger than or equal to L plus epsilon. Right, if something is true for every n sub k, then that same thing is going to be true for every n sub k sub j. Passing to the limit, I see that A is bigger or equal to L plus epsilon is bigger than L. And maybe you want to pause for a moment and write down the contradiction yourself. Feel free to do so. This is a contradiction as L is an upper bound on the set of subsequential limits of an. I'm going to pause for a second. All right, we're back. That was no delay for you, but it was a delay for me. Perfect. So we got a contradiction because while L is supposed to be an upper bound on the set of subsequential limits of A sub n, we've just explicitly constructed a subsequential limit which exceeds it, which is a contradiction. So what have we shown? Well, first we showed really immediately that for every epsilon and every m there exists some little n bigger than big N such that absolute value of a sub n minus L is less than or equal to epsilon. That is, L is a subsequential limit. And we've also shown that for every epsilon bigger than 0, there exists some natural number n such that as soon as little n is bigger than big N, then a sub n is less than L plus epsilon. That completes the first half of the proof. And maybe I'll even pause for a moment and say, so what do these two conditions together say? Well, we know what this one is. This one just says that L is a subsequential limit. Let's look at this one really quickly. So, what does this one say? This one says for every small number, there exists some big N, so eventually, so whenever little n is bigger than big N, that's what I mean by eventually, a sub n is less than L plus epsilon. So that means a sequence can exceed its subsequential limit, but it can't exceed the subsequential limit by very much and by very long. So a sub n might be bigger than L, it might even be bigger than L plus epsilon, but it can't be bigger than L plus epsilon forever. Eventually it gets sucked to be less than L plus epsilon. That makes sense? Or you can't answer me. So let's go the other way. Let's let a sub n be a bounded sequence. Let's suppose that L satisfies these two conditions. That for every epsilon there exists some big M such that whenever little n is bigger than big M, for every epsilon and for every m there exists some little n bigger than big M, so that a sub n minus L in absolute value is less than epsilon. And for every epsilon bigger than 0, there exists some threshold value big N, such that as soon as little n is bigger than big N, then a sub n is less than L plus epsilon. I want to show that L is the supremum of the set of subsequential limits. The way I'll do this is I will show two things. First, I'll show that L is an upper bound. Secondly, I will show that L is an L. Let's say why that will actually complete the proof. So what does it mean to be the supremum? So let's see. To be so 1 itself says L is an upper bound. That's good. If I want L to be the least upper bound, there's only one other thing I need to check. I need to check that it is less than or equal to every other upper bound. So let's let U be an upper bound. And what is an upper bound on? It's an upper bound on Blackboard bold L. Well, but let's see. 2 says that L is in Blackboard bold L. So that means L is less than or equal to U, because U is an upper bound on the set and L is in the set. Thus, L is the least upper bound. But the least upper bound on L is exactly what we mean by lim sup. So if I can check these two conditions, then I'm done. So, but remember that first condition, we've proven that this first assumption means that L is a subsequential limit. as blackboard bold L is the set of subsequential limits I get to conclude something. I get to conclude that L is in blackboard bold L. That's exactly the first of our two goals. Nope. Second of our two goals. So some more revisions of this bit of the tech document will appear. I can't do it right now because I'm in the middle of recording and I'm also out of town, so I'm away from my ability to make changes to the document. Oh, this is really embarrassing. Upper bound. So next, I need to show that L itself is an upper bound on the set blackboard bold L. So how will I do that? I'll consider any subsequential limit and try to show that it's less than or equal to L. Let A be an L, be any subsequential limit. I will consider any epsilon bigger than 0. So here's what I'm actually going to show. I'm going to show that A is less than or equal to L plus epsilon for every epsilon bigger than 0. That will mean that A is actually less than or equal to L. So let A be any subsequential limit of A sub n. Or consider any epsilon bigger than 0. There exists some subsequence which converges to A. Oh, that's problematic. Okay, so I did grab them all. So I'm not sure why the rest doesn't appear in this. You have them, the rest of the proof, in a document of your own. I'll finish the proof freehand right now. I apologize for this utter disorganization on my end. So there's a subsequence A sub n sub k which converges to L. Well, let's look at the two assumptions. Let's call this assumption B. So let's see, by assumption B, I fixed an epsilon and assumption B holds for every epsilon bigger than 0. There exists some threshold value big N such that for all little n bigger than big N, A sub n is less than L minus epsilon. And maybe I'll even be safe and I'll say A sub n is less than L minus epsilon over 2. Epsilon over 2 is positive, so I can still say that. Now let's go back to the sequence A sub n sub k. So let's consider any k greater than big N, then n sub k is greater than big N because it's bigger than or equal to little n. Maybe I'll add that. So A sub n is less than A sub n sub k is less than L minus epsilon over 2. That's enough information to pass to the limit. I have that as soon as little k is bigger than big N, that inequality holds. Since I have that, passing to the limit, A, the limit of A sub n sub k, is less than or equal to, notice even though I had a strict inequality before, when you take the limit you only get a loose inequality, is less than or equal to L, oh, those should be pluses, that should be a plus, L plus epsilon over 2, as this is true for every epsilon bigger than 0, because we considered any epsilon bigger than 0 and got that conclusion. We conclude A is less than or equal to L. L is an upper bound on the set of subsequential limits. Nice. So I've gone over by quite a bit, but fortunately I wasn't actually lecturing during this time. So this will be posted hopefully soon. Well, by the time you see it, it will be posted. Great. I will see you hopefully in class on Monday. Things seem to be pretty chaotic back home, but hopefully we will actually get to see each other again. Ciao.